All right. Hi, everybody. Thanks for coming. It's great to see you all. It is my great privilege to introduce Gianfranco Bertone. He and I last met, I think, in Sweden when we were talking about dark matter. So a quick introduction. He's a professor of theoretical astroparticle physics at the Center of Excellence in Gravitation and Astroparticle Physics of the University of Amsterdam. His affiliations include University of Rome at La Sapienza, Oxford Institute of Astrophysics in Paris, and he's also held position at Fermilab, Padova, another institute in physics, Zurich.
Yep.
So many locations. In 2011, he was instrumental in establishing the GRAPPA Center of Excellence in Gravitation and Astroparticle Physics in Amsterdam. And he's acted as the spokesperson of it until 2019. And from there until 2024, he was the founding director of the European Consortium for Astroparticle Theory, which aims to bring together a European community of theoretical astroparticle physicists and cosmologists. He's currently on sabbatical, lucky for us, at Columbia in New York City. And he's also acting as a fellow at the Italian Academy of Advanced Studies in America, which really sounds like a fascinating organization. And I think I know him best as the author of several books, including Particle Dark Matter, which is, I think I've recommended it to many of people sitting in the audience. But today we're going to hear about gravitational waves and dark matter. So welcome.
Thank you. Thanks a lot, Reina, for this very nice introduction. It's a pleasure to be here. It's my first time at Yale. It's incredible. I've never made to here, but I'm really happy to be here. So to see some familiar faces in the audience. Today, I want to tell you about gravitational wave probes of dark matter. Is there a way of making that kind of little text disappear from the top? But otherwise, don't worry. If it's easy, otherwise, don't worry, Reina. This is how I know that there are people in the audience who are not experts in dark matter. So I would like to start with a prologue on the so-called the dark matter narrative. What is that we talk about when we talk about dark matter? And then in part one of my presentation, I want to tell you about why I believe we've entered a new era in the quest for dark matter. And then in the second part, I want to tell you about the connection between dark matter and the booming field of gravitational waves. Okay, so let's start with this, with the dark matter narrative. If you go to a random conference on dark matter, you will probably hear two things about the history of dark matter. The first one is that the term dark matter was coined in 1933 by a Swiss-born astronomer whose name is Fritz Zwicky, who coined the term when discussing the velocity, trying to explain the high velocity dispersion of galaxies in galaxy clusters. And the only other thing we hear about the history of dark matter is that Vera Rubin in the 1970s then established the case for flat rotation curves, so dark matter in galaxies. My interest in the history of dark matter started when I was reading this paper by Zwicky in 1933. I just pulled out this paper by mistake, actually, because I was looking for the coma cluster paper. But this is another paper that Zwicky wrote a few months before the coma cluster paper in 1933. And if you look at what he writes, this is a paper about cosmic rays. It's called How Far Cosmic Rays Travel. He writes this sentence: according to the present estimates, the average density of dark matter in our galaxy and throughout the rest of the universe are in the ratio larger than 100,000. So this is 1933. This is before the coma cluster paper. Not only the term dark matter was in use, but there is an estimate of the local density of dark matter in the galaxy and an estimate of the density of dark matter on average in the universe. Okay? So we started to, I don't have time to go through the history of dark matter, but I just wanted to point out a couple of things that maybe are interesting for those of you who want to read more about this. Already back in 1904, 120 years ago, Lord Kelvin applied the kinetic theory of gases to the stars in the universe. The universe in 1904 means the stars in our own galaxy. And he wrote many of our stars, perhaps a great majority of them, may be dark bodies. And Henri Poincaré, only 2 years later, he wrote, when discussing the work of Lord Kelvin, he wrote, since the total number of stars is comparable to that which the telescope gives, then there is no dark matter. He wrote the term first in French, matière noire, and then in English, dark matter, or at least not so much as there is of shining matter. Therefore, he derived an upper limit on the abundance of dark matter in the galaxy. And then you might say, well, but maybe Zwicky was the first one to apply the virial theorem to a cluster of galaxies. But there is another not so obscure scientist who in 1921, Albert Einstein himself, applied the virial theorem to a cluster, not of galaxies, but to a cluster of stars in the Milky Way. And he obtained an upper limit on the abundance of dark matter in the Milky Way. You're trying to get rid of that text? Okay, thank you. And then it's only 1933, so a full, decades later, that Fritz Zwicky wrote his paper. And by the time he wrote that paper on the coma cluster, there were several estimates of the local density by people like Kapteyn and Oort and Jeans and others through the 1920s. And of course, the expansion of the universe had been the fact that we live in an expanding universe had been discovered thanks to the work of thanks to the data of Edwin Hubble and the work of Lemaitre and many others. So for those of you, I don't have time to go through the history, but I believe here in the slides a couple of references on a history of dark matter that we wrote with another practicing physicist, Dan Hooper at Fermilab. And for those of you who have an interest in the history of science, this is a work that we did with a professor in the history of science at the University of Amsterdam, Jeroen van Dongen, and Jaco de Svar, who's actually I think some of you might have met him. He's a postdoc at MIT now, and he's turning his PhD thesis into a book on the history of dark matter. Okay, so for those of you who have an interest in it, there's a long and very extremely interesting history for what concerns how we came to accept the existence of an unknown form of matter in the universe. The big question that we have in mind that we're trying to solve is, what is the universe made of? And I'm sure many of you will have seen this type of cosmic pie, where we usually say that if you take all the observations that we have about the universe, from the scale of galaxies, rotation curves, to clusters of galaxies with X-rays, lensing, and all the way to the CMB, the cosmic microwave background, and you further include, you can include type 1a supernovae, baryonic acoustic oscillations, any other observation you can perform, you get with this very strange composition of the universe. And I'm sure you've heard this. Only 5% of the mass and energy budget of the universe is in the form of atoms, matter that is familiar to us. 27% is in the form of matter, but not the kind of matter we're familiar with. It's matter that is not made of atoms, nor of any particle of the standard model. We call it dark matter. And there is 68%, which is in the form of dark energy, which is yet another mysterious substance that is responsible not for keeping astrophysical structures together. So it's not a sort of a scaffolding of the universe as dark matter is, but it's pushing the universe to expand ever faster. Now, this representation of the composition of the universe, I find it's a bit misleading if it's not qualified properly. If you ask the question, what is the universe made of, at different scales in the universe, physical scales in the universe, you get different numbers. If you ask what is the universe made of in this room or in a sphere around the Earth, you will find that almost 100% is made of atoms. And there are little traces of dark matter and even less of dark energy. If you draw a bigger sphere around the Milky Way on a scale of 20 kiloparsec and ask the question, what is the universe made of in this physical sphere of 20 kiloparsec, you will find that we start to pick up the contribution of dark matter from the halo of dark matter that surrounds the galaxy. And 28% is in the form of atoms. Only a small fraction of this 28% is in the form of stars. The rest is in the form of gas, mostly. It's only when you go to very, very large scales, on scales much larger than the scales of clusters of galaxies, that you recover this composition here, basically because you start to include a lot of empty space, right? Where you have you can pick up this contribution from dark energy. So if you want to understand what keeps a galaxy together, this is the kind of cosmic pie that you need to have in your mind. And even more importantly, you might be misled into thinking that there is something fundamental about the fact that 95% of the universe is dark. But if you look back in the history of the universe and ask the question, what was the universe made of during the first few minutes after the Big Bang, where all the helium was produced in the early universe, hydrogen and helium. The universe was the matter energy budget of the universe was completely dominated by relativistic particles like neutrinos and photons. Okay, so 100% known, we would say, right? These are particles of the Standard Model. Then the universe expanded, radiation was diluted very, very quickly. Relativistic particles were diluted very, very quickly. And if you look at recombination at CMB, when the cosmic microwave background radiation was emitted right after matter radiation equality, you start to see that dark matter dominates the energy budget, the matter and energy budget of the universe. Relativistic species are being diluted very, very quickly, photons and neutrinos you see here, and there's these atoms that contribute 12%. It's only today that you recover this contribution, this relative contribution that we were discussing, 68, 27, and 5. The universe has diluted so much, basically, that we start to pick up this this constant energy density that's contributed by dark energy that doesn't get diluted. This is the mystery of dark energy, a form of energy that doesn't get diluted, apparently, by the expansion of the universe. And if you look further in the future, far in the future of the universe, if this dark energy is something that looks like a cosmological constant, well, it will dominate completely the energy budget of the universe as all other species get diluted by the accelerated expansion of the universe. If you want to understand in physical terms what is going on, the best way of doing it is to plot the density of the various species as a function of the age of the universe. And then you see in orange, the dark matter, in blue, the baryons that are getting diluted just by 1/volume as the universe expands. And it's only very, very late that this dark energy contribution starts to dominate the expansion of the universe, just because the normal matter is being diluted by the expansion of the universe. If you're not familiar with all of this and just want to get like a visual understanding of why we trust that the standard model of cosmology, a model that includes these mysterious forms of matter and energy, is capturing something fundamental about how the universe works. This is a numerical simulation of the evolution of the universe. This is the time since the Big Bang. This is already 1.6 billion years. If you start from something, as your initial conditions, you take the cosmic microwave background, so the anisotropies that you see imprinted on the cosmic microwave background, you can follow basically how halos of dark matter form, how baryons basically fall into these big potential wells, and at some points, this the first generation of stars is born in these halos of dark matter. And as these stars process the intragalactic gas into heavier and heavier elements, you get a population of stars and a distribution of galaxies that actually really looks like the universe that we observe. And this is not just like a pictorial representation. From these numerical simulations, you can extract actually concrete information about the type of galaxies you form, how they are correlated in the sky, and things like that. Okay, so we need dark matter and dark energy in order to explain astrophysical and cosmological explanations on scales beyond the scale of our galaxy, basically. Already on the scale of dwarf galaxies inside our own galaxy, and then all the way to the largest scales in the universe. The big question, of course, for us is what is dark matter, right? What is the fundamental nature of dark matter? Now, we learned a lot about what dark matter is, especially what dark matter is not, unfortunately. But you can organize this information in the form of a 10-point test that a dark matter candidate has to pass, that any particle has to pass in order to be considered a viable dark matter candidate. So we will not walk carefully through all of these points, but let me just mention that in this first row, you have a number of observations about the total abundance of dark matter. The total abundance of dark matter in the universe is known with a precision around 1%. Okay, so we know how much of this matter we need out there, and this already sets interesting constraints on dark matter candidates, because you need to produce these particles in the early universe in the first place, so they can act as dark matter candidates throughout the evolution of the universe. We know that these particles need to be cold, and cold has a very specific meaning here. It's a statement about the velocity dispersion of these particles at the epoch of structure formation, or equivalently on the free streaming length of these particles. You can rule out standard model neutrinos as dark matter candidates based on arguments about how cold these particles are, how cold dark matter is. We know that dark matter needs to be neutral, so no electric charge, no color, nothing that will couple this particle effectively with the particles of the standard model. And then it must be consistent with all sort of other observations that we perform about the universe. It has to be consistent with Big Bang nucleosynthesis. For example, if you put some relativistic species early in the universe, it messes up completely the abundance of light elements that you produce in the early universe. And actually it has to be consistent also with stellar structure and evolution. It's very difficult to postulate the existence of new particles in the universe that don't destroy something in our universe, right? If you place a particle that is too light, with a mass that is comparable with the temperature of a star or a supernova, for example, these particles can be produced at the core of these stars and can act as cooling bridges. They can extract energy from the star and even destroy the stars in some cases. So you can rule out all these possibilities because we observe stars, we observe light elements, we observe stars, so we can rule out anything that would destroy them. And then there is a whole bottom row of constraints that you can set on how much dark matter particles interact among themselves. So on self-interactions of dark matter, the couplings of dark matter with nuclei, which is what people like Rayner, one of the things that people like Rayner study. And then there are constraints that come from the fact that we do not observe excess photons or synchrotron emission or antimatter from astrophysical structures. So we can rule out all dark matter models that, for instance, would annihilate with each other, particles that would annihilate with each other and produce photons or antimatter, or that would decay into photons. We can rule all of that out. In this 10-point test, there is a final, like a 10th point, which is more like a philosophical point, which is that if you want a particle to be a viable dark matter candidate, it needs to be possible to test the existence of this particle somehow, right? Maybe it's an experiment that you can perform 100 years from now, once we had enough technology, a good enough technology, but it must be in principle to run an experiment to verify its existence. Where does this leave us? Well, you can search for all the particles of the standard model. You can run this 10-point test, and all of them fail the test. Right? There's one or more of these points that are not passed by the particles of the standard model. There was some hopes until the 1980s that we would be able to explain the dark matter with standard model neutrinos, but we know that this is ruled out, and they cannot be all of the dark matter in the universe. So this is the perfect playground for particle theorists, because then you can be creative and propose the existence of new particles that may explain the dark matter. And this is where we are, more or less. This is a mind map of all the candidates that have been proposed so far. There's a complex landscape of proposals, and it would be pointless to go through them one by one. But let me just mention that these three blobs here, light bosons, and in particular the QCD axion, neutrinos, in particular sterile neutrinos, and weak scale particles, or weakly interacting massive particles, or WIMPs in short, they are the three classes of candidates that have attracted the most interest and attention in the past 4 decades, especially since the 1980s. There are still other possibilities. The dark matter is made of other particles. It is not described by any of these three big classes of candidates, or that it is made of microscopic objects. One of the questions that are often asked about the dark matter, is, could black holes explain dark matter? After all, they are, dark, and they don't interact much with other forms of matter. It turns out that astrophysical black holes cannot be the dark matter in the universe, but primordial black holes might, in principle. This is an old idea that people like Stephen Hawking and many others pioneered in the early 1970s. And I will say a few words about this connection later on. And then there is still this elephant in the room. There's the possibility that the evidence for dark matter is purely gravitational, right? So is it possible that instead of having GR as a theory of gravity and postulating the existence of other forms of matter, is it possible that GR is not the correct theory of gravity, or is only an approximate theory of gravity, and that we can reabsorb all of these effects that we attribute to dark matter once we have a suitable extension of GR? Now, for reasons that I'm happy to discuss later, I don't think that this is a very compelling explanation for dark matter. The universe really seems to behave as if there was GR plus standard model plus one species of cold collisionless particles. But until we find these particles in one of our experiments, one of our laboratories, I think we will always wonder whether the model that we have is really capturing the most fundamental nature of the universe. Now, what happened in the past 4 decades is that we've been searching for these particles, especially for these 3 particles in these 3 blobs up here, light bosons, neutrinos, and weak scale. And perhaps the class of candidates that attracted most interest in is this one. Certainly in terms of papers that have been written on it, this is by far the class of candidates that attracted most interest. And when I've entered this field, people would use WIMPs as synonyms of dark matter. I started my PhD in the year 2000, and people would say, we can constrain the number of WIMPs in the galaxy and things like that. Now, a program that lasted for several decades has started already back in the 80s and the 90s, and is still ongoing, where these WIMPs, these weakly interacting massive particles, were searched at colliders, at CERN in particular, with indirect detection experiments like Fermi, for example, and many other satellites searching for high energy emission. And with direct detection experiments, they were placed deep underground, and they were looking for the passage of these WIMPs through them. Now, so far, we've only obtained limits on what dark matter might be. So that's why I was saying that we know a lot about what dark matter is not, right? We can rule out entire portions of the parameter space of different theories. In the case of accelerators, we set lower limits on the mass of new particles that could be produced beyond the standard model of particle physics. And so typically these constraints are in the TeV range. In indirect detection experiments, we have exclusion plots in the parameter space that has on the y-axis the annihilation cross-section, and on the x-axis the mass of these particles. So we know that particles above these lines cannot be the dark matter. So a combination of parameters above these lines are ruled out by the fact that we do not observe excess emission of gamma rays from the center of the galaxies or from dwarf galaxies, for example. And in the case of direct detection experiments, we have constraints in the scattering cross-section. This is the WIMP nucleon spin-independent scattering cross-section as a function of the WIMP mass. And again, we have exclusion plots every time we run an experiment, and we find a number of events which is consistent with the background, the expected background in that experiment. We can rule out combinations of parameters that would give us a signal that we do not observe, a signal above the background that we do not observe. Okay, so the big question today is, where are these WIMPs? And to be blunt, we could ask the question, are WIMPs completely ruled out as a class of candidates in view of that? And my answer to this is a big, resounding no. And I'll give you like the order zero kind of explanation, but I'm happy to spend some more time on this if you're interested. So far, we have absence of evidence for these candidates, for WIMPs. But this is very different from evidence of absence, which is where we would ideally like to be, right? To rule out completely a class of models. There's still a lot of room, a lot of space in the parameter space of these theories. And, it's almost a practical sociological question, even before being a scientific question. How much time and effort are you willing to spend in order to rule out completely the parameter space of a theory? Okay, and as I said, for those of you who are interested, I have some more in-depth arguments I'd be happy to discuss. But what I would like to do now is to move on to the second part of my presentation, which is, where do we go from here? And I need to take a look at, do you have what time is it right now? Sorry, I don't, oh, this right over there, sorry, okay, perfect. So, I hope I conveyed the message that we are in a phase of profound transformation for dark matter studies. We've been guided by our theoretical priors, one might say prejudice, in the search for these particles. What do we do now that we haven't found these particles? Do we continue? When do we stop? And so on. Now, my perspective on this is that we should, and this is discussed in this paper here that we wrote a few years ago with Tim Tate. One is that we should broaden, improve, and diversify the searches that we perform. And I was glad to see that people here at Yale are doing just that. Another thing that I think has become very, very important is to exploit the new opportunities that arise from astronomical and cosmological observations. And there's a lot that can be done. After all, the dark matter is a problem that arose from astronomical and cosmological observations. The model that we have to describe all of these observations is too good to be, too perfect to be true, right? GR plus the standard model plus one cosmological constant and one species that is perfectly cold, perfectly collisionless, doesn't interact with anything at all. There must be a way to go beyond this kind of very, very simple description of the universe. And many surprises may come from upcoming astronomical and cosmological observations. Right these days, we're discussing some of these possible cracks in the standard model of cosmology. We'll see where this brings us. And if you're interested, well, I've worked a lot in this direction. I'm happy to talk more about that. But today I want to focus on the last point, which is how to exploit gravitational waves as a portal to search for dark matter. I want to start this discussion, this second part on how to use gravitational waves to search for dark matter, with a very kind of basic recap about black holes. Now, in general relativity, black holes are completely described by three numbers, all right? Mass, angular momentum, and charge. Now, this is often presented as, the fact that all matter that falls into the black hole loses memory about, what happened before the formation of the black hole. But if you think about it, the observed mass, distribution of mass, angular momentum, and charge, and also the redshift or the distance at which these objects are observed, it is drawn from a probability distribution that carries information about the history of these objects, how they were formed in the first place. And the second point I want to make is that these objects do not exist in vacuum. No black hole in the universe exists in perfect vacuum, right? There is an environment around them. This environment is what enables the electromagnetic detection in the first place. So if we can produce images like this, I'm sure you've all seen this, like a direct image of a black hole in M87, is because there's an accretion disk around it. Environments also affect the probability distributions of these masses, angular momentum, charge, and redshift. And if you think about it, actually, black holes were environments before being black holes, right? This is environment, this is gas and material that was out there that then collapsed and formed black holes. And the last point I want to make, which is what I'm going to spend the next 20 minutes on, is that this environment can also alter, in principle, the gravitational wave signals. Okay, and I want to establish this connection and argue, how we can hope to search for these environmental effects with the next generation of gravitational wave experiments. So the environments I will have in mind are of three types. The first one is an environment that I've just mentioned, and it's a guaranteed environment. This is the only thing of all the things that we'll discuss today that we are sure they exist, right? We observe accretion disks around black holes. Then I want to tell you about dark matter overdensities around black holes and why they might exist around black holes. And I also want to tell you about something that excites a lot of my colleagues in at least some theory departments, the possibility that dark matter is, that ultralight particles exist. Particles that are so light that basically their quantum wavelength is comparable with the size of black holes. Okay, and in this case, you can, this is another field that has a very long history, dates back to the work of Zeldovich and many others in the 70s. You can show actually that you can, if that configuration exists, an ultralight particle around a spinning black hole, you can actually show that you can extract mass and angular momentum and build a sort of an equivalent to the electron orbitals around the nucleus. You can build a gravitational equivalent of it with clouds of these ultralight particles around the supermassive black hole.
So if there is you see accretion disks, you know that there is a black hole, but I'm not sure other way around. Can it be a black hole without accretion disks?
It is in principle possible. Sorry? Well, it depends on where they are, right? If they are in the galaxy, in an environment which is rich with gas, gas would fall onto them.
There's no distance.
What do you mean?
There is no distance, right?
That's right. Or at least it would be extremely faint.
Right. So basically, it's not one-to-one correspondence.
I agree. No, when I said that it is guaranteed, is that not that every black hole will have one of these around them, but it's certainly something that we know exists in nature, right? It's something that is realized in nature, and you can ask the question, how much the presence of an accretion disk would modify the gravitational waves, right? Okay, so the work that I'll present is done by these wonderful people here. These are all students and postdocs that were or are currently in Amsterdam, and all the credit for the technical work that I present goes to them. I will try to put their photos and their names prominently in all the plots, so you see who's worked on that. Now, we said that accretion disks we can observe them. How about the other environments? Do we expect dark matter to be around black holes, and why? If so, why? Now, this is again a field where attracted interest of many people through the decades. Let me give you like the short version of the story, and I'm happy to tell you more if you're interested. We know that black holes exist with a very, very large mass at the center of galaxies, right? Now, the way we understand the existence of these monsters at the center of galaxies is that they started with a small mass, from a small seed mass, and then they've accreted a lot of matter, and they've grown up to the size of 10 to the 9, sometimes 10 to the 10 solar masses. What happens to the dark matter? Suppose that you have a seed black hole here with sitting at the center of a large concentration of dark matter. Think about the black hole at the center of our own galaxy. We know roughly how dark matter is distributed at the center of a galaxy. This is the density, and this is the distance from the center of the galaxy. The density goes roughly like r to the -1. This is, for those of you who are in the field, the so-called Navarro-Franken-White profile. Now, let's grow adiabatically the mass of the black hole, and let's see what happens to the density of particles. Now, for those of you who care about some of the details, you do this by conserving the so-called adiabatic invariance, in particular the radial action that is conserved under adiabatic transformations. But basically, if you grow the mass of the black hole adiabatically, you pull in all the dark matter particles, and then you can compute what is the change in slope of the profile due to this adiabatic compression of dark matter, of the dark matter halo. Okay, and you can actually compute things analytically. If you start from an r to the -1 slope, you can compute what is the final slope. So this introduces two scales in the problem. The first one is the scale of the black hole, the size of the black hole, or if you care about the dynamics of dark matter, the ISCO, the innermost stable circular orbits. But if you want to have another scale in mind, this is the event horizon of the black hole. And there's another scale, which is the radius of gravitational influence of the black hole. So the volume around the black hole, which is dominated by the gravitational potential of the black hole itself. If you put an r to the -1 slope in the initial profile, you can actually derive analytically, under some assumptions, the final slope. It is something like that goes like r to the -7/3, like r to the -2.333 something. So very, very steep. So this is one of the ideas that people have put forward to create these overdensities. Another possibility is around primordial black holes. The way you form overdensities of dark matter around primordial black hole is different. The idea is that you start from a homogeneous distribution of dark matter and black holes, and at some point, as the universe expands and dilutes its density, these particles at some points will decouple from the Hubble expansion, turn around, and cluster around black holes, already deep in the radiation era, as a matter of fact. And there are many, many authors who've studied analytically and numerically how this process happens and what is the predicted slope in that case. Now, one of the interesting things is that in both processes, whether it's adiabatic compression of a dark matter halo or particles decoupling from the Hubble flow, around primordial black holes, you form very, very large overdensities of dark matter, so large that if dark matter is made of annihilating particles, they would produce an enormous flux of photons, high energy photons, antimatter, and all sorts of other things. And the fact that we don't see this excess emission allows us to set very stringent constraints, actually, on the properties of these particles. And let me skip this in the interest of time, but let me, if some of you are interested in the connection between particle dark matter and primordial black holes, ask me to come back to these slides. There's a point that I would like to make about that, but it takes me maybe a few minutes to go through it. Let me go a bit faster here. So I've argued that we have at least a couple of ways of forming large overdensities of dark matter around black holes. What are the observational consequences? What could be potentially the observational consequences of that? Well, if you have a black hole sitting at the center of this dark matter halo and dark matter all around it, then you can ask the question, what if I have a secondary object that is merging with the primary object in presence of dark matter? Now, imagine that you're sitting here on the big black hole and you're watching the secondary object go around you. What you would see is something like this. You see out of your window the secondary object moving and interacting with all the particles of dark matter. This is a black hole, and it's moving in these, just plowing through this distribution of dark matter. Now, Chandrasekhar in the 1930s has worked out this problem. This is what is usually referred to in astrophysics as dynamical friction. You can actually show that because of symmetries, all the forces orthogonal to the direction of motion basically cancel out, all the difference in velocities. But because of this forward-backward asymmetry, there's a drag that is experienced by the object as it plows through this distribution of matter. So in practice, what you get is this orbit of this object is experiencing a drag. So when you want to work out the energy losses in the problem, the orbital energy losses, there is a component that comes from gravitational wave energy losses, and there is an additional term that depends on this process here. This is what is called the dynamical friction, referred to as dynamical friction here. And for those of you who care about details, you can write down an evolution for the separation of the binary, and there is the standard term that you can find in all textbooks about how this system evolves in presence of gravitational waves. And there's another term that comes from dynamical friction, which depends on, it's directly proportional to the density of dark matter you're plowing through with your secondary object. Now you might think, it's quite easy to capture the physics of this problem. You write down this equation, you solve it, you plug in this dark matter profile, you get a result. It's not so easy. The reason for that is that you're transferring, so where does this where do these energy losses by dynamical friction come from? Well, there's a transfer of energy because of these gravitational interactions from the binary to the dark matter distribution. You can actually compute how much work is done by these energy losses. This is the total work done by energy losses by dynamical friction divided by the binding energy of dark matter particles around the black hole. And what you can see is that depending on the parameters that you choose to solve this problem, this work done by dynamical friction can even exceed the binding energy of dark matter. So basically what is happening is that you're steering the dark matter distribution very quickly with this secondary object. And this dark matter distribution is being heated up, and all these particles are being ejected basically by the system. Now, there are many other details, relativistic corrections, role of eccentricity, and so on. I'm happy to tell you more about that if you're interested. But so that you can visualize the problem, this is a numerical simulation of two black holes surrounded by dark matter particles. And we put them on a sort of a collision course so that they would, these are highly elliptical orbits. So these two objects will come, if they were in presence of Newtonian interactions only, they would come very close to each other, and then they would go back to where they started. But if you look at this, if you look at what happens, you will see that these two objects are getting very close. Now we're going to zoom in a bit. And if you check at what happens here, you will see that the separation gets drastically reduced. The binary doesn't go, the secondary object doesn't go all the way where it started. The separation is reduced and the orbits are circularized by this process. But check also the blue particles all around. There's almost nothing left here. Let me rerun this so you can see. Just take a look at what happens to all of these blue particles here. You will see that as these two objects interact very violently with each other, a lot of these particles get enough energy to be basically kicked out by the system. Okay, so this is an example of a dramatic energy exchange. Now, doing things like this is extremely difficult. You know, to do analytical work on this is very, very difficult. And also because it's the process is so violent, it's unlikely that we can, well, it's complicated to say something robust about the presence of dark matter. So let me consider, and in the next 10 minutes or so, I want to talk about this. Let's consider the system where this M2 mass is much, much smaller than M1. So you have a small object orbiting around a very massive black hole. Okay, well, in that case, you can solve analytically or semi-analytically the problem if you're careful enough. So if you're not familiar with you know, this formalism, don't worry. I just wanted to show you a couple of things. You remember we had an equation for the separation of the binary that had two terms, one from gravitational waves, another one for dynamical friction losses. What I want to draw your attention to is that in a more complete description of the problem, the dark matter density that enters this equation is a time-dependent quantity. Okay, so you cannot just solve the system as if dark matter was just, you know, sitting there doing nothing. You have to solve at the same time one equation for the separation of the binary, the evolution of the binary, and one equation for the density of dark matter, or equivalently for the phase-space distribution of dark matter. And it took us a while actually to formalize this problem, but now we have a pretty complete model that follows the evolution of a binary in presence of dark matter, including the feedback on the distribution of dark matter. The effect that we search for is shown in this image here. This is a kind of a pictorial visualization, and then I'll show the actual scientific result. The idea is the following. If you have a binary in absence of any dark matter around it, it will produce a waveform, okay, that we can detect on Earth. If you add dark matter around the central black hole, you will have again a waveform, but this waveform will be slightly dephased compared to the waveform in vacuum. And actually, if you accumulate enough cycles, if you observe this waveform for long enough, you can actually pick up the small but cumulative defacing induced by dark matter or any other environment on the waveform. Okay, how big is this effect? You can actually quantify this in terms of number of cycles. So the number of cycles is just the integral of the frequency. And you can calculate the difference between the number of cycles in presence of dark matter with respect to the case where the system evolves in vacuum. And you can actually show that for realistic values of the parameters of the system, this number of cycles can be very, very large. It can be, you know, 10 to the 4 or 10 to the 5 for a system that in total has 10 to the 5 or 10 to the 6 total. So it's not a small, I mean, it's a small effect, but because it's cumulative, you can pick up the signal from actual data. Now, from this alone, you wouldn't be able to say whether the signal is detectable or not. You have to run a full kind of Bayesian analysis. And this is what we've done with a number of... Sure, Kiara. Yeah.
It depends on this black hole spins, right? Because if you have these spinning black holes, you get post-Bertonian contributions.
That's right. All right.
A different number of wave cycles that you would measure over an observation time.
You're-
So how is that different from what you're
You're absolutely right. I'll give you like a short answer to this, and then maybe we come back in the discussion session. Now, for the moment, everything that I'm presenting is in absence of spins. There are arguments that one can make, and no self-interactions. Actually, these are the things we're after, right? You know, the kind of things we hope maybe one day to measure. But to go in the direction of spins, this is all, you know, Schwarzschild black holes, because we needed to start from somewhere. I'm optimistic that even when we include spins, it will still be possible to discriminate these effects from the GR effects included by spins, because of a very peculiar behavior of these systems, which is that these effects are important earlier on in the evolution of the binary, but then become almost completely irrelevant in the final phase, right? So the evolution with frequency of the dephasing that would be induced by these environmental effects is not the same that would be induced by spins. This is the intuition, but we still have to, you know, we're not there yet, but we hope we're going in that direction. We will soon have full relativistic waveforms, and hopefully I can answer this question with actual numbers. But you're absolutely right.
Just if you,
Yep.
so basically you have difference between two circles.
Mm-hmm.
Delta N is different between two ends that are found from theory.
Yes.
So just trying to understand. So to tell something about the halo or whatever dark matter does, one needs to have a reference number.
Of course.
Really, measurable reference number for one of the two quantities.
Of course.
I don't understand. Is it
No, but that's why I said, you know, from this only, this would not be enough to claim anything, right? You know, for the moment at this stage, it's only a theoretical difference between two different cases that, as you say, cannot be directly inferred from an observation. But this is the next step, which is a fully Bayesian analysis. So you can ask the question, if I give you one waveform, right, you know, detected at LISA, you know, with one of these future interferometers, would you be able to tell whether there is an environment or not, right? And if so, what are the parameters of this environment? And this is the next thing that I want to show you. Let me show you directly this. That's it. That was exactly the question we were after. You know, is there any observational handle that would allow us to say, yes, there is an environment here. These are the parameters of the environment. And this is this work, actually, that I can show you here. Do you mind if I come back in a couple of minutes? Hopefully, I will answer your question, because I need to go through another environment, and then I show the comparison between different environments and why I think it's possible to discriminate among those. So far we talked about this environment here, this dark matter over densities. We know, as I said, that accretion disks are observed in the universe. So we need to make sure that if we attribute some of the effects we observe to one of these environments, we need to make sure that we're not confusing these effects with the effects that would be induced by something else. And I wanted to also briefly go back to this case of gravitational atoms. So the case of accretion disks has been worked out by a number of people now. There are numerical estimates, there are analytical estimates. The consensus here is that the main effects, if there is an accretion disk around the central black hole, is that gas induces torques on the binary. And this is very similar to what happened in planetary migration, where you form these massive objects at large distances, and then because of torques, they migrate further in. You can make predictions in this case too, for the dephasing as a function of frequency. In the case of gravitational atoms, the situation is still different. I don't have much time to, because I only have 5 minutes left. I don't have time to discuss this in detail, but feel free to ask me questions. I just wanted to point out something. For these objects, we have now a series of papers that computes the so-called ionization power. So the energy losses induced by this gravitational atom on the binary. Okay, so just like we did the calculation in the case of dark matter over density, We have analytical and numerical estimates in this case too. And now at this stage, we can combine these three different things and address your question, precisely your question. How do we extract information about the environment from an observation without having any reference value from first principles, basically? Now, what you can show, let me show this first, and then I'll go back to the previous one. What you can show is that you can generate, for example, mock LISA data, mock waveforms. So we put ourselves in a case where there is a dark matter dress around the black hole. We generate the waveform, and then we build a full Bayesian analysis and try to reconstruct that waveform with a vacuum template where there is nothing, there's no accretion disk, no gravitational atom, no dark matter overdensity around it. We try to reconstruct it with in this case, with the correct templates where there is a dark matter dress, with a template where there is an accretion disk, and with a template where there is a gravitational atom. So for each of these mock data sets, we try to reconstruct it with no environment at all, and with three different environments, and ask the question, would we have enough information in the data to claim that there is an environment? And the answer, and I'm happy to walk you through the various cases, but the answer is always yes. So these gravitational wave experiments, in absence of spins, would have enough information. There's such a clear evolution of density with frequency. If you want a binary system in vacuum, is such a simple system because of what GR is. The black holes are two numbers, basically. They behave really like particles more than astrophysical objects. The evolution of frequency is so characteristic, it's so well understood that you would have enough information that if you see a departure from that prediction would directly point to an environment. Not only it would point to an environment, but if you reconstruct the defects, and if you try to interpret the defects in terms of the wrong environment, then you get a Bayes factor, which is always very, very much in favor of the correct environment. Okay? So my time is almost up. I just wanted to show you one final slide. Do I have time for one slide and then I'll close? Do you want me to wrap up or 60 seconds? Okay, because this is going to be on the archive tomorrow, and this is actually something I wanted to also discuss with Priya. So I'll just show you very briefly. All the calculations that we had so far assume that the black hole would grow from an extremely small mass, basically a zero mass seed. But of course, black holes in the universe don't grow from zero mass. There's always something that happens in the universe. These objects can form from population 3 stars, from the collapse of population 3 stars, or from supermassive stars. Now, if you form a star before forming a black hole, then you can actually show that you don't get this this kind of constant slope type of profiles. You get something which is more rounded at the top. And then once the star collapses to a black hole, you get yet another modification of the profile. And the characteristic scale here that we're introducing is basically the size of the star that gave rise to the black hole in the first place. And this is the plot that you will find tomorrow on the archive, where you see the dark matter density as a function of the distance. And these are the 3 different profiles I talked about today. The yellow one is the profile I mentioned as the first one. So this assuming that the size that the black hole grows from a zero mass seed. The red line is what you get from the collapse after the formation of a supermassive star, and the blue line is what you get after the collapse of the star to a black hole. So hopefully, as we improve our modeling of these systems, we hopefully get enough information about the systems to have good enough templates and to extract the signal eventually from the data. Okay, so my time is up. A couple of quick take-home messages on this part. and then proper conclusions. Take-home messages, the era of precision gravitational wave astronomy is coming. Gravitational waves are powerful probes of black hole environments, and there is the possibility to investigate the particle nature of dark matter. This is connected to the question that Priya was asking, can you check for self-interactions? Can you check for self-annihilations? This is a very powerful handle on this, and I'll be happy to tell you more if you're interested. A couple of final thoughts, since there are many young people here in the audience. This is a time of profound transformation of dark matter studies in view of the absence of evidence of popular candidates, and I'm insisted that this is not evidence of absence. Many of these experiments that we're running might still reserve surprises, but it's also important to diversify their dark matter searches, to exploit astronomical observations and gravitational waves. And I spent actually most of my time speaking about this connection. One example about the connection with gravitational waves. And in general, my impression is that the field is completely open, and this is an extraordinary opportunity for you, and new generations, to come up with new ideas and discoveries. Thank you.
Thank you, Gianfranco. Questions?
Yes,
so when you were talking about in the limit where, so not in the limit where there's a small object rotating around the black hole, but in the limit where we have a binary system and they're both pretty big,
yep,
and they impart energy onto the dark matter that's then radiated away. It seems like that that scenario was kind of dismissed in favor of the limit where there's a small object, but I was wondering if that dissipation of dark matter, it reminded me of when you were talking about how dark matter could be produced in the core of stars and how it would radiate energy away from the star and change the life cycle of the star. It would be a deviation from what we would expect without dark matter. So I was wondering if that would have a similar effect on the like energy profile coming from a binary system like that we could detect?
Yeah, no, it's a great question. We've been thinking about that. So I can tell you a couple of things. So our interest and the reason why we run that simulation was mainly driven by work on primordial black holes. We wanted to connect, we wanted to understand. So there is a sort of a consensus, I would say, that primordial black holes with a mass around 10 to 100 solar masses cannot really be all of the dark matter in the universe because there are so many different constraints on them. But if these objects exist in the universe, they might exist at a subdominant level. They might be a small fraction of the dark matter. Now, there was a big question, of course, whether LIGO had observed these primordial black holes. And what we were thinking is, there were some estimates about the merger rates of these objects. We were thinking if they carry a dark matter dress around them, this would likely change the merger rate history of these objects, which is why we run those simulations. Now, it turns out that there is an effect because it changes the separation and it changes the ellipticity of the orbits. But these two effects actually go in opposite directions. So the net effects, because you reduce the separation, so you increase the merger time. Sorry, you reduce the separation, so you reduce the merger time, but then you circularize them, so you kind of increase it. If you put the two things together, the global effect is not very large. And then there's always, going back to the other question, what do you compare with, right? If you have an observed merger rate that is 10% difference from the one that you would get in absence of these effects, would you even realize, right? And other things might be, if it's true that many of these objects carry a dark matter dress, would it change the predictions for the background of these black holes? So there are ideas in that direction. We're focusing on this one because this is really more like precision physics we have more control on, but the field is completely open.
So thank you for a great talk. Just being a thermal pessimist, I just want to bring up three concerns. The first one is related to the adiabatic growth, right?
Yes.
Universe is a violent, hierarchical growing place. So black holes merge. That's why we see gravitational waves. And whenever they merge, then any pre-existing dark matter dress will be destroyed through the three-body scattering. So you only can build up at the very last stages. So that's a concern. The other concern is.
Would you mind to respond? Would you like me to respond one by one, or at the end?
Just rattle off my three concerns and then.
Okay, sure.
So the other one is, you're sensitive to waveform that's indicating some matter around the black hole, but when you adiabatically grow your black hole, which sits at the center of a galaxy, you'll adiabatically grow your stellar component around it. So your dress will be both dark matter and baryonic matter. So not clear what you're going to learn about dark matter.
Yep.
And the third one is related to the dynamic of friction. If I was not mistaken, the way you've treated the dynamic of friction was through sort of diffusive approach with a diffusion coefficient, which is based on sort of two-body scattering. But this really becomes a three-body problem. You have to really take into account that you have that other black hole there, and that you're going on resonant orbits. And in that case, people have shown that dynamic of friction becomes a very complicated resonance-driven proposal. So my question, this last one is a question where you have thought about how you can treat that.
Yes, okay. So I'll try to give reasonably short answers, but I'm happy to chat after the talk at length about this, because these are three concerns that we've had in the back of our mind for a long time. It still have at some level. So starting from the first one, black holes merge. If they merge, well, we've seen what happens when two black holes merge. They tend to completely ionize the distribution of dark matter around them. Now, a couple of things. So together with David Merritt, like a few years ago, we were looking into the effect of mergers on the stability of these dark matter overdensities. You really need equal mass mergers to be able to disrupt successfully these objects. A mass ratio of 1 to 5 or 1 to 10 will decrease the dark matter, but not destroy it. Okay? So ideally, and this is, it is in this direction that we're going, we would like to embed these calculations into a proper cosmological framework and calculate a realistic history of mergers. Unfortunately, nobody knows really how this happens. So I think realistically, we're going to have to work out, and we have, actually, I can show you one case in which we worked out the number of objects that did not experience major mergers in the context of a numerical simulation. All right? You're absolutely right. These results would apply only to those unmerged objects, right? And not to the ones that experience major mergers. If 99.999% of the objects experience major mergers, this is something we will never observe. About stars, this is another, it's a field of research, right? Nobody can really make predictions about, how many stars are left in a halo. I can tell you a couple of things. The presence of stars would modify the dark matter distribution. So for instance, I'm always going back to the work that we were doing a few years ago, addressing all of these concerns systematically with David Merritt. So we have simulations in which we co-evolve the dark matter and the stellar distribution. And actually you can show that, depending on the parameters of the system, the most frequent case was that you tend to lower the dark matter density because of transfer of energy from stars to dark matter particles by maybe 1 order of magnitude. It's very model dependent, so it's difficult to attach numbers. But when you go very, very close to the black hole, you don't expect stars to survive like 10 Schwarzschild radii from the black hole, right? And inside the closest, inside the orbit of the closest star, dark matter particles are so bound to the central object that they barely notice that there is an object, orbiting out there. And the third one was?
Three-body issue.
The three-body issue, yeah. So we've spent, months, trying to quantify these effects, one by one systematically. In the end, we have some analytical estimates, but maybe more importantly, we have numerical simulations. So we've run these systems with numerical simulations, and we painstakingly compared all the numbers that we have in our semi-analytical models, including one of the biggest effects was on that there is Coulomb logarithm in the dynamical friction. you know, if you take something a la Chandrasekhar, you know, it doesn't work at all. We had to play a lot with it. Now we're at a stage where I trust these calculations to the degree of precision that is required for making these comparisons, or to the level of precision that is required before post-Newtonian corrections kick in. And now we started like a whole project basically where we want to refine things, including all of these post-Newtonian corrections, and eventually merging all these efforts into what needs to be done in any case, which is to do relativistic, you know, fully relativistic waveforms. And there, even in the case of vacuum, you know, Embry systems are very, very difficult. But it's, you know, it's down the road. So we're getting encouraging results from all of this before it becomes like the main thing that we do. You know, we want to get convinced that this is worth the effort, of course.
We have one last question.
First of all, thank you for your talk. And I have actually a two-part question about dark matter accretion on primordial black holes, for example. As you mentioned, primordial black holes may be a fraction of the overall black holes and dark matter. So I was wondering whether it makes sense to think about a mixed dark matter scenario, and whether this mixed dark matter scenario, having like such a wide landscape, would have an impact on the environment you are probing, and if there's a possibility to, you know, differentiate between single component and multi-component dark matter. And like as a subsequent question, I was wondering also, since these affects also the Halo evolution, would it make sense to also look at galaxy and gravitational wave clustering, spatial clustering, since there are bias tracer of this dark matter distribution? By putting constraint on this bias parameter, we could also put constraints on those dark matter models. So these are the two questions.
All right.
Yeah,
okay. So for the first question about mixed dark matter, I can tell you a couple of things. So, well, first of all, if you have primordial black holes with dark matter around them, this will be already a case of mixed dark matter, right? Now, was your question in the direction of asking, what if instead of one type of particles around the primordial black holes, you have more than one? Now, then it depends what kind of particles. If they are cold collisionless particles, like axions and asymmetric dark matter with a mass of GeV or so, then these particles will be very, very cold. And whatever the ratio of their omegas, so the abundance in the universe, you would most probably find the same ratio in the density around the black hole. And the final results for these things basically wouldn't change at all. A more complicated case is when you have something like cold collisionless particles, like in those overdensities of dark matter, and these gravitational atoms. Because in that case, their density is not just scaled just by the ratio of the omegas, they're completely different. And in that case, it becomes more difficult to extract the signal, because you have two environmental effects playing out at the same time. Fortunately, there are no good reasons, I think, to believe that you would have three components of dark matter with a similar omega, with a similar energy density, especially if they are candidates that do not arise from a common origin in the early universe. So I'm not particularly concerned. But if you wanted to do, like, if you wanted a quantitative answer to your question, you would have to rerun the whole thing with multiple environments at the same time.
I think I'll wrap it up for today. Thank you so much.
Thank you, everyone.